A ball is thrown from ground level with a speed of v. Let's just make that v naught. That's the initial velocity. At an angle of theta up from the horizontal. For what value of theta will the ball land the farthest away? Well, this is an interesting problem. We're actually not given numbers, but we're given variables, and we're supposed to try and figure out what value for the variable will maximize the distance thrown. So what's going on here? So you can throw something at, so from ground level, you can throw it at a very small angle, you could throw it very steeply. Is there an angle at which you get the maximum distance? So let's draw a picture here. What's going on? We are throwing from ground level with some initial velocity, v naught, at some angle theta. So what's it going to do? We expect it to go up and then down, symmetrically, like a parabola. But the question is, at what theta will we maximize the distance? We could certainly imagine that if we throw it horizontally, it's already on the ground, it's not going to go anywhere. And if we throw it straight up, it will go straight up and come down and not go anywhere horizontally either. So maybe there's some angle in the middle between 0 and 90 degrees where we get a maximum distance. We're trying to maximize then the distance that it travels like this. Let's again define our axes at the initial point of the ball. Because it's on the ground, it'll be right at the origin. And hopefully we have a good handle on the equations. That I'm not going to put the equations up. Maybe you can remember what they are. But we're going to proceed in a very similar way that we have before. Let's write down the variables, and then we'll take the problem away. So what are the variables? Again, x naught, x, v naught x, vx, ax, y naught, y, v naught y, vy, ay, and t. So what's x naught and y naught, or what are x naught and y naught? We know they're both 0. We're starting at the origin. What is x? Well, x, that's again what we're looking for. We're trying to maximize x. But we do know that y, because it's coming back down onto the ground, y is 0. What are v naught x and v naught y? Well, maybe you can guess from what we've already done before. V naught x, in terms of what we're given, will be v naught cos theta, and v naught y will be v naught sine theta. Vx, Vy, well, we don't know. We don't know what it's going to be doing when it lands. Ax, 0. Ay, negative. For the moment, let's just call this negative g. Negative g, negative 9.80 meters per second squared. Just so everything else is a variable, we'll just leave that as g. And t, we don't know. How are we going to solve this? Again, we're going to solve this the same way we did before. We'll use the third equation for y to solve for t, and then we'll take that t and put it in the third equation for x to solve for x. Okay, let's do that. Let's see if we can do that using purely variables rather than having any numbers in there. Third equation from the y motion, we have y equals y naught plus v naught yt plus 1/2 ayt squared. But we know that y and y naught are both 0. So we have 0 equals v naught y. V naught y is v naught sine theta times t plus 1/2 ay is negative g t squared. We don't have a constant term in this, so we don't actually need to solve this using the quadratic equation. Let's bring the negative term to the other side, and we'll write this as 1/2 gt squared equals v naught sine theta times t. One solution of this equation is if t equals 0. We'll have 0 equals 0. So one of the possible solutions is t equals 0, which makes sense. Y, the value of y is 0 at the initial time, t equals 0. So that makes sense. Assuming that t does not equal 0 allows us then to divide a t off, which leaves us with dividing off a t. Dividing off 1t leaves us with 1/2 gt equals v naught sine theta, or dividing by t multiplying by 2, t equals 2 v naught sine theta over g. Now, to the third equation for the x motion, we have x equals x naught plus v naught xt plus 1/2 axt squared. But we know x naught is 0, ax is 0. What do we have? X equals v naught x is v naught cos theta times t, and t is 2v naught sine theta over g, which leaves us with x equals 2 v naught squared sine theta cos theta over g. Now what we want to figure out is what's the maximum value of this. As theta varies, what's the maximum value that x can have? Well, let's notice we've got something 2 sine theta cos theta. Well, that's a trigonometric identity that's equal to sine of 2 theta. So we can rewrite this as x equals v naught squared sine 2 theta over g. So where is this a maximum? For what value of theta will we get a maximum value for x? Well, that's actually pretty straightforward. Notice that if theta equals 0, or, well, let me back up for a second. When is sine of an angle equal to 0? We know that sine looks like this at 0 and 180 degrees. So when the argument is 0 or 180 degrees, sine is 0. Well, to be 0 or 180 degrees, that would be theta is equal to 0 or 90 degrees. If theta is 90 degrees, then 2 theta would be 180, and sine of 180 would be 0. So that means when theta is 0 or 90 degrees, x is going to be 0. But that's what we said at the beginning of the problem. If the object is thrown horizontally from ground level, it's on the ground already, so it's not going to go anywhere. If theta is equal to 90 degrees, it's going to go straight up and come straight down, and x is going to be 0 also. But when will this be a maximum? Well, when is sine of something a maximum? It's a maximum when its argument is at 90 degrees. Well, when is 2 theta equal to 90 degrees? When theta equals 45 degrees. So when theta is 45, that's when we'll get a maximum displacement. Well, that's kind of interesting. So that when this is thrown exactly in the middle at 45 degrees, that's when we get a maximum displacement. And what's the displacement going to be in that case? Well, sine of 2 times 40, sine of 90 is 1. The maximum displacement will be, x max, will be v naught squared over g. Very, very interesting result. Okay, let's try one more problem.